Hello, my name is Mark King, and you are listening to the seminar series that I sponsor in my role as Atlantic Canada representative of the International Association of Hydrogeologists, the IAH. In this capacity, we solicit seminar presentations from speakers all over the world. The general topic is groundwater and hydrogeology, but within that field, the talks can vary over a wide range, from water supply to geochemistry to remediation to the fate and transport of groundwater contaminants and beyond. And at times we may also stray outside the bounds of hydrogeology when a particularly interesting technical topic or speaker comes our way. Welcome to our seminar series. My guest today is David F. Boutt. Dave is an associate professor of hydrogeology in the Department of Geosciences of University of Massachusetts-Amherst. He has a BS and an MS in geology from Michigan State University and a PhD in hydrology from New Mexico Institute of Mining and Technology. In his research, Dave focuses on incorporating hydrogeological information into detailed hydrologic budgets. He has worked throughout the U.S. and also in Japan, Sweden, Chile, and the Caribbean. In today's seminar, Dave presents an analysis of long-term records of groundwater levels in the Northeastern United States, and he attempts to decipher regional-scale groundwater surface water interactions. This rich data set contains a story of large droughts, climate teleconnections, and significant changes in groundwater storage.
Okay, thanks a lot, Mark. Today I'm going to talk a little bit about the work that we've been doing using some long-term instrumental, basically water level measurements in the northeastern United States. And really what we're trying to do with this study is to see what we can learn from looking back at sort of how do aquifer systems respond to past sort of climate variability, and thinking about how these different aquifers respond in terms of their geologic characteristics as well as their sort of position in the landscape and how well coupled they are to various pieces of surface water. So I'd just like to acknowledge some funding for this project was part of sort of a USGS, National Institutes of Water Resources competitive grant. Had a number of students work on this on these projects throughout the year, and they're listed there. So one of the main reasons that we are interested in groundwater surface water interactions in the Northeast U.S. is that we've had a lot of sort of past impacts of land use and climate change on stream flows, and there's a lot of interest nowadays to understanding or better providing water for quote-unquote ecological services. And in Massachusetts and in a number of the other northeastern U.S. States, there's a large push now to limit or to enforce the amount of surface water in streams. And the real question here is, how do the different basins respond to different amounts of sort of management in terms of how much surface water there is available for stream flow, and how does that impact aquifer system. So in the glaciated Northeast, typically we have unconsolidated sediments on top of fractured crystalline and metamorphic bedrock, and in a typical valley type setting we might have evidence or deposits that reflect or standing bodies of water that were there, laying down lacustrine sediments that are draped on top of a sort of a vast history of deglaciation sediments in the form of deltas and outwash plains that interact in a very heterogeneous framework in 3 dimensions on top of this sort of very old weathered bedrock surface. And one of the questions that we've been working on is trying to understand how the regional scale distribution of these very heterogeneous deposits impact groundwater surface water coupling, as well as how these different aquifers respond to different types of climate variability. And sort of the second question as part of that is, what implications do these distributions, these deposits, have for stream base flow distributions, and how do these stream base flow distributions respond to interannual climate variability? So, for today's talk, I'll briefly go over a little bit of background on New England hydroclimatology, give you a little bit more geologic context, and really go into the heart of the talk, looking at processing of all this instrumental data that we've pulled from publicly available sources and trying to make sense of those pieces of data in the context of what we know about the hydrogeology. Look at a little bit of how that impacts surface water, groundwater interactions, and offer some conclusions from these studies. So there's a lot of interest in understanding how climate change is going to impact not only air temperature going into the future, but also the distributions, the amount and timing of recharge in different types of aquifer systems. So we've already started to see about a 1/4 degree C increase in temperature per decade on all of our instrumental temperature sites throughout New England. Most of even the conservative models suggest that we're going to see, an increasing temperature over all seasons, and as opposed to places like the Southwest U.S., which are very dry, places like here in the New England states, projections suggest that we're going to get actually increases in precipitation, both on an annual basis, predominantly in the form of winter precipitation. We've already started to see there's lots of anecdotal evidence of earlier spring ice out date in lakes, timing of higher river flows becoming earlier in the season, lots of ecological suggestions that the climate has already started to deviate from what it was. One of the things that we'll use as an indicator in this talk is this is a composite of all New England weather stations average for area of total annual precipitation as a function of year going up to about, I think, 2009. And we're starting, we've been seeing this increase in precipitation over time. It's unclear if this is necessarily related to sort of global warming effects, but it's had a large impact on sort of the functioning of the hydrologic cycle. One of the big events in here that you can see in terms of the big drought occurred in the 1960s, and we see evidence of this drought in all of the time series records that we'll talk about in this talk. Just a brief overview of the hydroclimatology of the region. Interestingly enough, so this is a plot here of precipitation distribution throughout the year. The blue line here is precipitation. The dashed lines are plus and minus 1 standard deviation. One of the things that you can see is that precipitation is fairly evenly distributed over the year, almost at a rate of about 100 millimeters per month. There is a significant amount of variability in terms of the precipitation, but the distribution is fairly even or uniform throughout the year. And that's opposed to the potential evapotranspiration as just computed with a simple relationship between air temperature and PET based on latitude. You can see that it peaks in the June, July months and then falls off towards December, towards the colder months. And one of the things that this leads to is it leads to a very distinct seasonal cycle of both stream flow, and stream flow is also influenced, of course, by the warming of the environment and melting of of water stored in the form of snow on the land surface. But one of the things that you can see, especially in this plot in the later months, is once PET sort of ratchets down and we have leaf drop, you actually see a rise in stream flow and a rise in the water table. So essentially the water table, the hydrology, the storage in the subsurface in this region is strongly controlled by this sort of P minus PET signal, and not as much by sort of, you know, annual variability in precipitation. So one of the things I mentioned is that this region, and this is fairly typical for sort of glaciated regions underlain by fairly hard rocks, is that we see a lot of heterogeneity in the distribution of glacial deposits from one location to the next. You can go from these alluvial fill valleys that might have on the upwards of about 100 meters of glacial sediment up onto some of these ridge tops that might be on the order of a couple meters thick of surface tills. You know, it's just sort of a graphical distribution of some of these deposits that we'll be talking about. Tills are very poorly sorted. A lot of the tills here in the New England area, because of the parent material is very hard, they tend to be fairly sandy, are very poorly sorted. Some of the sand and gravel deposits are some of the most productive aquifers you can find in the world, with, you know, hydraulic conductivities on the upwards of 100 meters per day in some of these environments. As you move, let's say, from a deltaic environment into sort of near one of these inputs of sediment, you can see that the grain size decreases significantly. And in a lot of these valleys, in the center of these valleys, have some lacustrine deposits. These are deposits associated with proglacial lakes and such, all underlain by a fairly heterogeneous distribution of hydraulic conductivity in the bedrock, mainly dominated by fracture porosity and permeability. If we look at a spatial distribution on the order of, let's say, on this scale here, about 2 kilometers, you can see these different colors. This orange would be well-sorted fluvial glacial deposits. The greens here are thick tills on these drumlins, thin tills outside of those drumlins, and sort of very thin till on top of bedrock. And it creates this very heterogeneous distribution of hydraulic properties on the order of, you know, hundreds of kilometers. And really, part of the work that I'll be showing here in a minute is trying to understand how this distribution of hydraulic properties impacts the water level response, as well as the amount of base flow that's driven to streams in this type of environment. So in detail, our study approach was to look at monthly distributions of temperature, precipitation, groundwater data. These are water table observation wells that were installed for one purpose or another that the USGS has taken over, and is part of what's called a climate response network that's maintained in the U.S. These sites are specifically chosen to minimize direct anthropogenic effects, and the sites that we've been working on, you can see them here in this the right part of the screen. The black dots are wells. You know, blue dots here are precipitation stations which are co-located with air temperature, and then the orange symbol here are stream gauge data. One of the things that I think you'll see from this distribution, it'll come out later in the talk, is we don't have an equal amount of coverage in our water table observations, with a lot of our data set biased towards southern New England. So I'll focus a little bit more on that area in the talk. So as I said, southern New England has about 80 of the 120 wells that we investigated in this study fall in this region. The different color dots here just reflect red being an alluvial aquifer systems. In the southeastern Massachusetts, the Cape Cod area, and islands, there's a broad outwash plain, part of the Plymouth Carver aquifer system and the Cape Cod aquifer system. This is an environment where there was a large outwash plain, some large proglacial lakes, and as you'll see later, for the purposes of the analysis, I've separated out these data points and treated them differently than sort of interior alluvial valley fill aquifers, which have a lot more. They tend to be thicker and not as laterally extensive. So one of the first things that we've noticed when looking at all of the data, so this is on each of these plots, you'll see elevation of the water table as a function of time. Note here that the time scales are different in each of these plots, but they all pretty much go back to the early 50s when groundwater monitoring first started kicking up. And actually, a lot of the data sets that we've been using were wells that were put online during the 1960s drought, which was a very large hydrologic event in New England. We see a large majority of water levels in these records showing increasing water levels over time. Some of them are very peculiar. This well here, it appears to be sort of a high threshold in terms of the water level will reach some high, but that high is actually increasing over time, suggesting maybe a connection with some surface water, as opposed to this site here in Till. Its low is increasing over time, which is a little bit of a different response, and then one that sort of oscillates about some increasing average. There are fewer sites that we looked at that had decreasing water levels. Both of them that I'm showing here are in outwash deposits, and these, if you look at the elevations of the water table above sea level, these are coastal settings, and both of these wells are out on Cape Cod. So and one of the things we'll talk about in a minute is that there seems to be some correlation in the data set between groundwater removed out of storage due to for public drinking water supply and declining water tables here. So to take a little bit better look at the trends that we see in these water levels, we use this statistical approach called the seasonal Mann-Kendall test, and basically it's a fancy trend testing analysis tool that looks at season to season trends. And basically, you are comparing, say, the August water level of 2006 to the August water level of 2007, and repeating that over the data set. And so we get an output of this of the data set indicating if there's a trend and what's the magnitude of that trend at a given confidence interval. And for all the data that I'm showing here, these are at the 95% confidence interval. Here's an example of a well in Lakeville, Massachusetts that shows one of the largest increases in water level over the record, almost on the order of 20 or 30 centimeters over that time. So as I showed you earlier, we have a large number of sites showing increasing in water level, some sites showing decreasing. We've looked at spatial trends between precipitation, which if you can look, and now I'm looking specifically at trends since 1970. And one of the reasons we chose to look at trends since 1970 is if we go back and look at the trends in water level since when a lot of these records came online, they came online right during a very large drought in the 1960s, and that tends to bias the trends, in my opinion, towards positive trends. So we chose a 1970 start date for this analysis because it's, I think it honors the data a little bit more. One of the things that you see is that pretty much either the precipitation at these gauging stations is increasing or it has a flat trend. There are no negative trends in precipitation since 1970. In stream flow, we see more flat trends than anything else. And then if you look at groundwater, there's quite a lot of variability. A large number of sites showing fairly large trends, increasing trends in the water level, which is consistent with precipitation. And some sites, a lot of them in sort of the southeast Massachusetts area near Cape Cod, which is in fact a sole source aquifer system, which it makes sense that if we're going to see an impact on water levels, groundwater levels in these areas, that they're going to be impacting this growing area of sort of coastal southeast Massachusetts. One of the things that is puzzled us and other researchers that have been looking at stream flow trends in the New England area is that stream flow, if you just look at total stream flow throughout the year, seems to be flat or actually possibly have a negative trend, and that's at odds with these increasing precipitation trends. And it turns out that if you look at 7-day low flow base flow or 7-day low flows in summer, for some of these data sets, other researchers have found that there is a trend in those data sets, which is consistent with what we've been seeing in these groundwater trends. So,
Dave, I was assuming that some of those flat to decreasing flow trends might be due to just the role of these watersheds as maybe water supply taking place upstream or something like that, or are these watersheds kind of isolated from that?
Yeah, in the stream flow records I'm showing, those effects have been minimized because of the site locations. There are plenty of examples where that's occurred, and that's one of the hard things with we're trying to go and mine these existing data sets. So it would be nice if we were designing this experiment ourselves to go out and place a gauge on in the same watershed that we have multiple groundwater wells, but we just don't have that luxury with going back and looking at these data sets. So I think, Mark, that effect has been minimized somewhat in the stream flow records, but maybe not necessarily in the groundwater trends. So as I said, there's a number of people that are trying to understand what's causing changes in stream flow in New England, and there seems to be a consensus that base flows are increasing, and there are some suggestions that fall precipitation has been increasing as well. That's sort of caused some of these groundwater levels to be higher than they would be.
Okay.
So we're going to shift gears a little bit and take a little bit closer look at the groundwater records and see if we can pull any more nuggets of information out of them. And one of the things that we spent a lot of time doing is doing some time series analysis or some signal processing to remove, let's say, in this case, the annual signal out of, as I said earlier, there's a really strong annual signal in these water level records. And so here's a raw, this is a data set from just an example well here showing the head change over time. This record started in the 60s and goes until present. This is the raw data set. What we do is we take in this plot here, we calculate what's called an anomaly, and this is basically, an I here would stand for an individual record in some month. So what we would do is we take the value of the water level in January, let's say, of 2006, and subtract off the mean level in January for the whole record. So what we do is we try to remove that seasonal trend and and look at the sort of lower frequency trends that are recorded in this record. And what that does is, for this example, see here, there's a multi-year drought here in the 80s. You can see a decrease in water level. When we remove the seasonal signal from that, shows up as this nice decrease in water level. One of the other things that we do is we normalize by the standard deviation to look at something called a normalized anomaly. And what that allows us to do is compare different types of records to one another. So not just anomalies in water level, but look at anomalies in stream flow and anomalies in precipitation. It should be noted here that we use a 12-month moving average, which is this red line, on top of our sort of the raw anomaly data, which are the blue dots here, and that helps us look at multi-year trends. So here's an example for a piezometer nest in Pelham, Massachusetts, which is close by the university here. This record goes back to 1985, and the reason I chose this one because it has a very compelling record showing some very anomalous behavior. But here's precipitation. These are normalized anomalies. The way to read this is, each unit, 1, 2, and 3, is 1 standard deviation, 2 standard deviations, 3 standard deviations. So you can see there's a lot of variability in precipitation. Let's look at this early 2000s drought that we see in this record. You can see this dry period here, a little bit sort of anomalous precipitation, this little trough here. We see that in the stream flow. We see it in this unconfined aquifer, which is, again, these are, this is not part of a research site. It's part of this monitoring network. So the stream and the monitoring wells are not necessarily located in the same subbasin, but they're still in the same sort of larger watershed. So you can see this nice progression of the precipitation drought recorded in the stream flow, recorded in the sort of the lowering of the water table, both in this unconfined aquifer and in the confined bedrock aquifer. One thing that I think your eye can see pretty easily is this time lag and how the systems respond. And we've done some work trying to use this sort of phase shift or this time lag to help us estimate how well connected the streams are to the aquifers, as well as possibly understanding something about the hydraulic properties of the different types of aquifers and how well connected the unconfined aquifer is, let's say, to the confined bedrock aquifer below it. So we did this analysis for all the sites that I showed you earlier, and this is just a summary from this GRL paper that was published a couple years ago now. So we have temperature record here, precipitation, stream gauge, stream flow, and groundwater. And one of the things that we were really pleased with when we first did this analysis is that all these records are internally consistent with one another, right? So we see, if you look again at this big 60s drought here, we see that really light up significantly in precip and stream flow and then the groundwater sites. One of the other things, each one of these red lines is an individual site, and the black line here is the average through all of the sites over the whole region. One of the things that struck us and was the subject of this GRL paper is that the groundwater sites show, in terms of the anomalies, a much larger variability in the response. And one of the conclusions that we came to in that study is that this is due to the sort of the heterogeneous hydraulic nature of the subsurface aquifers. And so you can see that there's a consistent amount of variability in how these sites respond, and that'll be the subject of a couple more plots that I'll show you here in a minute. So what I'm going to do now is compare the precipitation, the stream flow, and the groundwater sites, their mean lines, all on top of one another in a composite plot. So I'm looking at sort of, these are New England average anomalies, if you will. Okay, so as we go, a larger number here, a more positive number is wet, negative number is dry. This is the precipitation minus the potential ET record for the time. You can see these 60s drought, and there's a number of other big droughts that show up in these records that are well known. And actually, there's on average there's about a drought, a fairly sizable drought, about 10 years every 10 years in this area. So if I put on the stream flow data set, it lines up very nicely with the precipitation as one would expect. You can see here that there is, as we showed earlier, there's a little bit of a time lag in terms of when the precipitation anomaly becomes its minima and when that minima occurs in the stream flow in the system. And then if we throw on the groundwater anomalies, you can see this progression of sort of, an anomaly in precipitation leads to a larger anomaly in the stream flow, to a larger anomaly in the groundwater records, especially during the droughts. And you don't necessarily see that occur during the wet periods, right? So the stream flow anomalies and the groundwater anomalies they're better coupled when it's wetter than they are when it's drier, and that has to do with stream groundwater interactions that we'll talk about in a second. So, and these are fairly repeatable, and the 60s drought we spent some time on because it's the largest event in the system. And in general, what we're seeing when we're looking at these data sets is that things are becoming, we're seeing the more and more positive anomalies compared to the wetter anomalies, and again, suggesting, and this is consistent with some of the recent years of precipitation that we've seen, it's getting quite a bit wetter. So what I'm going to do now is I'm going to make just a cross plot of the stream flow and the groundwater to look at their distribution with respect to one another. This plot here is plotting the groundwater anomaly versus the precipitation anomaly. And you can see that they're fairly well correlated. But one of the things that's interesting is when we plot the groundwater anomaly and the stream flow anomaly against one another, what you see is that we have this trend where as the groundwater anomaly becomes more and more negative, as it becomes drier and drier and drier, the stream flow anomaly begins to sort of reach its limit. And essentially what this is telling us is it's telling us as the water table drops, the stream flow can become no less than that, and essentially as an anomaly becomes much more negative or more negative, essentially the streams will dry up. So some of the other work that we've been doing is spending a little bit more time looking at how these water levels how the water levels are influenced by the hydrogeology of the system. So this plot shows water level as a function of month. Each of these blue lines are water levels in sand and gravel and these alluvial aquifers. The black and the orange line here are water levels in the tills and in the bedrock. And one of the things that you can, I think, see here pretty clearly is that there's a fairly tight clustering, that the seasonal variability in these sand and gravel aquifers are very distinct from the till and bedrock aquifer system. So, and I'll just quickly fly through some of these plots. These are water table anomalies for the bedrock wells. Again, a positive number here is a wetter time. negative number here is the drier time. One thing to pay attention, I'm going to flip through these really quickly, but one thing to pay attention to is these are all going to be all on the same scale, but just the magnitude of the oscillations here. So we're going from about, plus 1 meters to, let's say, -1, -1.5 in the bedrock. The till shows a very similar range, shows a very strong multi-annual 2 to 3 year cycle in the water levels. Okay, this is for till, plus 1 meter, -1 meter. Outwash plains, this is southeast Massachusetts, Cape Cod area. One of the things that you can see is there's not as much variability. There's a more tight clustering of these sites, and a larger dynamic range in terms of the whole data set, but definitely not as much. If I go back to till, you can see the till and compare and contrast these. There's not as much high frequency sort of variability. And finally, going to the alluvial aquifers, they show the sort of smallest dynamic range, maybe from 0.5 to plus 0.5 to minus 0.5 range. So if we compare all these on top of one another, I'm just going to quickly, this is just the mean of those data sets compared to one another. One thing that you can see is the till and bedrock show a significant larger variability in terms of their response to these climate, these changes in precipitation. I don't have this plot in this slideshow, but the specific yield that we've estimated from the tills and the specific yield of these alluvial aquifers, because the tills tend to be fairly sandy, their specific yields tend to be on the average of maybe about 0.2 to maybe 0.25. The specific yields for the alluvial valley fill, which is this red line, tend to be about maybe 0.25 to 0.3, and that's not great enough to explain the difference in these water level anomalies. Because remember, I'm not looking at essentially storage; we're looking at changes in the water level. So it's not great enough to explain that difference, and we think that's because of how the tills are in the recharge area primarily, and the alluvial aquifers tend to be down in the valley, lowlands, and better coupled to stream flow. So one last analysis that we performed with this data set is to do some wavelet analysis. So what this allows us to do is to pick out signals in the data sets and compare them to one another. So what you're the way to read these plots is that this is on the y-axis here is a period of the signal in years, plotted as a function of time. Anything outside this, what we call cone of influence here, anything to the sort of below it is a signal that is much greater than the position on the plot. So if we go down here, we can't resolve 30-year signals in a 60-year data set, essentially. And the brightness of the colors here basically means that 2-year signal is very, very strong. Let's say for this example here, and there's a strong 4 to 8 year signal. This signal that's coming up in the precipitation, and you can actually see it in the alluvial valley fill, maybe not as much in the till. This is related to El Nino, ENSO type variability, potentially in the Pacific. So these are reflecting changes in teleconnections between what's happening here in New England and what's happening to sea surface temperatures in the Pacific, as well as we think there's actually a North Atlantic oscillation record that's in some of these precipitation signals that then propagate into the aquifer systems.
Dave,
yep.
Just in terms of interpreting this plot or reading this plot, can you explain again what you mean by periods here and physically what that relates to?
Well, okay. So yeah. So in terms of the wavelet analysis, it can be related or it's similar to a Fourier analysis where you're trying to extract a component of a cyclicity in the, let's say in this case, the water level fluctuations that are, on that have a period of 2 years or a period of 4 years or a period of 8 years, let's say.
Right.
And you're trying to pull out the strength of that signal compared to noise. Okay, and on this right-hand plot here, each one of these dashed lines is a significant threshold. So in this case, if you just look at the till record here, so this is for the whole data set. So that's why we call it a global peertogram. So basically, it's what is the dominant signal in what is the period of the dominant signal in, let's say, the till water level record. And so you can see this sort of orangish, yellowish dashed line that there's a signal here at, sort of between 2 and 4 years that its strength is greater than that of sort of just noise in the system. Okay, so what that means is that there's a strong sort of let's call it 3 year. There's a strong 3 year sort of signal in that data set. If we go back and we look at this the till record, you can see sort of this high frequency component of the signal that is on the order of 3 or so years, where it goes up for 3 years, it goes down and goes back up and down. And so what we've been trying to do with this wavelet analysis is to try to look at what periods are dominant in these records, and can we relate it to sort of hydrogeologic functioning. And it's clear that the till records are very distinct from the alluvial valley fill record, and we think that is a consequence of their location in the recharge area, as well as their sort of thin, they tend to be fairly thin. They tend to be located in the uplands of these watersheds. So it's telling us something about the hydrogeologic setting of the aquifer system. So, and you can see that all of these, if you look at the signals in the precipitation, which is this blue line here, you can see that they all, when there's a strong signal in the precipitation, there's a really strong signal in the in the aquifer system, but they have different powers. So basically, the alluvial valley fill aquifers, because they're so permeable and they're at the downstream end of these watersheds, they tend to filter out the high frequency sort of 2 to 3 year periods, and only you can see here that this 4 to, let's say, 8 year period is strong. And not to say it's not there, you can see it, but it's not statistically significant. So I'm going to wrap up the talk. I've probably got too many slides here, but I'm going to wrap up the talk on talking a little bit about trying to look specifically at interactions between groundwater and surface water with these data sets. So there's been some really interesting sort of fun little back of the envelope type calculations that people have been doing, that was introduced by Heitzema in '95 and Heitzema and Mitchell-Brucker, where they've looked at the ratio of sort of how much recharge a system gets, let's say an aquifer system gets, relative, so it would be this recharge component here, relative to how thick the aquifer is and how permeable the aquifer is. So if you have a system that is, let's say, low permeability, and it receives a lot of precipitation, the actual precipitation, okay, schematically shown here, so let's say the theoretical precipitation here would be RP, and the actual would be RA, or recharge, let's say. would be the actual recharge would be much lower than the potential recharge because the water table is high. It's very strongly connected to the surface water system. Where if you Heicherman worked this out in sort of a dimensionless form, where when this quantity is greater than 1, basically the water table is very close to the land surface, very strongly connected to the dense surface water network, and basically throws or provides a lot of water to stream systems. Compare that to another case where the recharge, let's say the potential recharge is equal to the actual recharge, meaning that in this case you have deep water tables. When recharge comes into or precipitation comes into the system, recharge comes into the system, it can take that water, and then it can move that water in a more sort of regional sense, and we call that recharge controlled water table. So the quantities that I think you should focus on here is this. So we're really looking at the ratio of recharge to hydraulic conductivity. Okay, when either the recharge is high or the hydraulic conductivity is low, the water table is shallow, it's close to the surface, it's very well coupled. You don't have a lot of what's called, you don't have a lot of regional flow. When this quantity is low, we call it recharge controlled, and you have a lot of sort of regional long flow paths from where the water comes into the system to where it leaves. So Tom Gleason at McGill has been doing a lot of fun work with this water table ratio. Okay, again, he takes the log of that quantity and has been mapping it both over the United States, and he's also got some work where they've been mapping it over globally to look at the distributions of the regional recharge control versus topographically controlled. Again, what's important here is these more positive numbers. The blue ones should suggest the water table is closer to the surface, and there's a lot of interaction between streams and the aquifer system. If you look at places in the Southwest and Central Valley and Colorado Plateau area, you see that this ratio is very, very negative, and basically it's due to decreases in recharge, thick aquifers that are fairly hydraulically conductive. So we've tried doing this analysis and comparing it to some of the data that we've been working with. So here's a map that Lily actually put together, looking at the water table ratio for Massachusetts. Okay, so again, blue here are areas where the water table is going to be high. Red areas here, water table is going to be low. These are short flow paths. Okay, short, low, very, very low residence time flow paths, and this is going to be longer, higher residence time flow paths. So one of the interesting things that comes out of this in some of the deltaic areas of Massachusetts here in the valley, as well as in Cape Cod and southeast Massachusetts, they show up as having more recharge dominated flow. So we could compare that to depth of water and the water table ratio, which is that ratio of recharge to hydraulic conductivity for our data set here. And you can see that there's some correlation between depth of water and the water table ratio, which is what we would expect for this system. So the next step, what we wanted to do with that is to estimate, can we compare the water table ratio quantity to estimates of base flow from our data sets and compare that to our groundwater system. So we took all of our stream flow data and used a very simple digital recursive filter to estimate base flow. This is a common technique used nowadays to come up with a sort of very first order base flow estimate by filtering out the high frequency signal and focusing on low frequency signal. As you can see, it looks very similar to our stream flow, as you would expect, and correlates very nicely with our groundwater database. So just taking our base flow estimates from our stream gauging sites in Massachusetts and comparing that to our water table ratio, we actually see a really interesting correlation between our predicted base flow index and the water table ratio map. Essentially what this means is that our topography controlled systems, okay, they have a shorter flow paths, they have lower residence times water, we have a very strong connection from the hill slope to the stream, resulting in sort of less base flow to those systems. In terms of, over the year, there's going to be a stronger component of quick flow, stronger component of stream flow in these systems, and compare that to areas where we have a higher base flow in these in these areas where the water table is deeper and larger base flow indices, which is actually quite a pleasing result. So in the interest of time, I think I'll go ahead and wrap this up because I'm looking at 48 minutes here. So just to conclude on our work, looking at these long-term instrumental records, one thing I'll comment is that there's not a lot of places in the U.S., yet the world, where you can do such a long or use data sets that have periods of record, especially for groundwater systems that are this long. So it's quite a unique data set that I hope people will continue to work with. And one of the things it's telling us is that especially in this area, the water table to this wet and dry periods is highly variable in both space and time. And a lot of this is telling us something that we already knew, but it's also very pleasing that we can go through this analysis to try to pull other pieces of information out. And it's essentially that these aquifers are very small, and there's a large amount of heterogeneity in how groundwater and surface water are coupled. You can't just assume that. I was actually shocked when I moved from the western part of the U.S. to the eastern part of the U.S. I thought I would never see a losing stream again, and it turns out that there's plenty of places where you can find losing streams in this very humid environment, and a lot of it has to do with the hydrogeology. So coming back to we're looking at our trend analysis. More than half of the wells have long-term increases in water level, and they don't necessarily correlate with P-E trends. And I think a lot of this has to do with potentially changes in land use, land cover, as well as increases in precipitation that are allowing for more recharge to occur, which has important consequences for people trying to manage the amount of water in streams. The frequency content showed you with the wavelet analysis and the time series are unique for the till and bedrock compared to the sand and gravel aquifer, and I think it has to do with the hydraulic properties being very distinct between those two, as well as the fact that the till bedrock recharge mainly occurs in the uplands and shows a much higher frequency, a stronger correlation to, let's say, multi-annual precipitation variability. And and finally, we looked at the data sets that compared the stream flow anomalies to the groundwater anomalies, and they can be decoupled from the regional water tables during exceptional droughts. And I think that's something that needs to be considered and remembered when trying to manage groundwater and surface water surface water reserves or resources sort of in a single context. So, thanks. Are you still there, Mark?
Yeah, I sure am. Sorry, I had myself muted, so I didn't disturb you. But that's a really interesting study, Dave, and an interesting approach. Do you know? Are you aware of if it's been done elsewhere in the U.S.?
Well, as I said earlier, there are not many other places where you can do this because with time series that go back 40 and 50 years.
Sure.
So there's been a lot of interesting work done in, of all places, Illinois, where Illinois has invested a lot of money and time in their monitoring system, not only for groundwater, but also soil moisture. They have a very dense network, and there's been a number of researchers that have used that network, that long-term network that they've been developed to look at sort of the hydroclimatology. The one thing that wasn't really emphasized or explored a lot in Illinois is the sort of the role of the subsurface heterogeneity and the distribution of different hydraulic properties. I think a lot of that's due to the fact that the geology there is not that heterogeneous throughout the area. And so yeah, and there's been some studies in the UK and in the Netherlands that have looked at similar type of sort of time series analysis, looking at response. There's another study that comes to mind in Spain where they've looked at time series analysis and trying to analyze both precipitation and groundwater response.
Any idea what they see in terms of precipitation trends in other places around the globe?
Oh, in terms of precipitation trends, there's a number. I can't think of. There's been a lot of work looking at stream flow trends in the eastern half of the U.S. The group out of Princeton, and then there's a gentleman at Tufts, Richard Vogel, that's done a lot of work looking at trend testing and stream flow, and I think I'm trying to recall off the top of my head as far as trends in precipitation, they're definitely not as strong as what we've seen here in New England. And if you look into the literature and think about and see what people are thinking for how climate change is going to impact different parts of the world, I think that a lot of people are thinking that as the hydrologic cycle becomes more intense, the dry places are going to get drier and the wet places are going to get wetter. There's a group out of Huey and Woods Hole and MIT that have been trying to compile records, water level records from ponds in Massachusetts and in the Northeast, and they've actually found that the last 100 to a couple hundred years, the water table has been as high as it's really ever been, which is pretty crazy.
Yeah.
To think about, I'm talking about records that go back 10,000 years. There was a woman named Paige Newby that just published a GRL paper that was looking at correlations between sea surface temperatures and precipitation and water levels in ponds in Massachusetts going back 10,000 years, I think. So, one of the concerns is that, there's two concerns. One is that it's been really, really wet. Even the last, 300 or 400 years have been anomalously wet. So there's there's some people that feel like we're in a hyperpluvial system, and that we've been, and all of our sort of water resource supplies are built on, it being fairly wet here. And the concern is, is there a potential for us becoming, drier in this part of the world for a lengthy period of time? And I think some people think that might be the case. The other one is, when people are trying to manage, let's say state regulatory agencies trying to manage how much water is in streams and, how much water should be in a certain stream, they are taking a very sort of stationary approach to looking at these problems. And they're, I think being able to look back and assess, come up with some predictable tools for us to try to understand, what's gonna happen in the future. So
you mentioned a couple times about groundwater and surface water becoming decoupled during drier conditions relative to wet conditions. I'd like to make sure that I understand that process. Is that basically because the base flow is dropping to zero at some point?
Yes, yeah, or stream flow. If we go back to, and there's let's see, yeah, like this plot. So there's a paper out there by Eltahir and Ye. Pat Ye, who's now at I think University of Tokyo in Japan. That they actually worked on that Illinois data set, and I think the title of their paper is like asymmetric response of the water table to droughts and floods. And basically,
so that's the relationship you're showing here.
Yeah, and they showed the same thing, where as the water table drops, the effective wetted area of the streams becomes less, and base flow decreases to, in some areas the streams can become completely dry. And I guess it's similar to the variable saturated area concept, right? As the water table becomes higher, there's more, where the water table is closer to the surface, then it becomes essentially, it becomes wet and generates streamfall. And if it's not, there's not as much streamflow generated. So that's what I mean by that plot. And we've spent a little bit more time. That relationship primarily comes out of essentially this plot. I mean, that is that data that I'm showing there. So, you can see the anomalies during these driest times are much, the values are much different, more negative than the stream flow. But, when you look at the values of the anomalies during the wet times, I mean, they're right on top of one another.
Sure.
Yeah. So this is that asymmetry that's going on there. In an arid environment, this concept really only works when you have base flow being driven to streams by groundwater, right? So this is a concept that's applicable in a humid environment with primarily gaining streams.
Understood. Dave, I'd like to thank you for your time today and an extremely interesting presentation. And before I let you go, I wonder if you could tell me if anyone has any more questions, anyone in our listening audience with regard to your talk, would you be receptive to them contacting you directly, say by email?
Oh, sure. Yeah, no worries. And, we've got a paper in review right now in Journal of Hydrology that has a lot of this stuff in it. And there's a paper in GRL that's cited in the talk, and a master's thesis that came out of this work. And this research is ongoing, so I'm sure there'll be more peer-reviewed literature that will come out of that. Excellent. Yeah, I look forward to seeing that. And so, what's your email address? Yeah. So DBOUTT at geo.umass.edu.
Thanks a lot, Dave. Look forward to hopefully seeing you again next month in Chile.
Okay. All right. Thanks, Mark.